So hello guys and welcome to my channel. Today again I am back with important numericals on high voltage engineering. And here today in this lecture we will discuss some important numericals that we have left in our previous lectures. So here the very first one is here: a 132 kilovolt transmission line is terminated by a transformer at a substation and the transformer is protected by a arrestor operating 120 kilovolt located at the incoming lines, and here the basic impulse level with a stand voltage of the transformer is chosen to be 500 kilovolt, and the protective ratio PR required for the transformer is 1.2. Here the protective ratio is given as 1.2, and check whether the transformer is properly coordinated with the arrestor if a lighting stroke of 8000 kilovolt is incident at the arrestors. And here the relationship between the discharge current and the residual voltage is given by Vd equals to K into Id to the power beta, and arrestor data is given in the tables. And here we have the data of arrestor given as discharge current and its respective residual voltage is given. So for 10 kilo ampere the residual voltage is given as here 300 kilovolt. Similarly for 20 kilovolt the residual voltage is given as here 360 kilovolt. So starting with the solutions, here we know the relation is given here: Vd is equals to K into Id to the power beta, and here we have used this relationship. So Vd equals to K into Id to the power beta, and in place of Vd here we can see for 300 kilovolt and for 360 kilovolt. So for 300 kilovolt Vd equals to here 300 equals to K into, and in place of Id here we will use 10 kilo ampere first. So 10 to the power beta, and here it will be K equals to 300 upon 10 to the power beta, and here we have equation A. Similarly, if we use this 360 kilovolt, its current discharge current will be 20 kilo ampere. So 360 equals to K into 20 to the power beta, and so from here we will get the value of K as 360 upon 20 to the power beta. And once we will solve the value equation 1 and 2, will get 300 upon 10 to the power beta equals to 360 upon 20 to the power beta, and from this relation we will get the value of beta as here finally taking log on both sides we will get the value of beta. Here we have beta as 0.263, and similarly from equation 1 we will get the value of K as K is equals to 360 upon 20 to the power 0.263, we will get 163.73, and given the BIL of transformer. So in the questions the basic impulse level of transformer is given as 500 kilovolt, and again VW is given as 8000 kilovolt. Similarly protective voltage VP is given as 120 kilovolt. These all things are given in the questions. And so now discharge current, in order to calculate the discharge current, here we have the formula ID equals to 2 into VW minus VP upon Z. And since here the value of VD and VP is already given in the questions, and here the Z is not given, so for overhead lines we will take the value of Z as 400 ohms. So ID will be 2 into, in place of VD we have 8000 given minus VP as 120. So in place of Z we have 400, so we will get the value of ID as 39.7 kilo amperes. So VD will be K into ID to the power beta, and we have obtained the value of K. Similarly we have obtained the value of ID, and similarly we have obtained the value of beta. So just substitute all the values here, we will get the value of VD as 431.05 kilovolt, and also the protective ratio is given as 1.2. This is also given in the questions. So the required BIL will be this VD into this protective ratio. So 431.05 into 1.2, and this is going to give 517.26 kilovolt. So here we can finally conclude that the required BIL, here this is the required BIL, means 517.26 kilovolt, and in the questions the BIL is given as here given basic impulse is 500 kilovolt. Since the BIL of transformer is 500 kilovolt, but the obtained BIL is given as 517.26, so the required BIL is greater than given BIL of transformers. That's why insulation is not properly coordinated. So similarly here we have the next one as it is necessary to obtain a tower footing resistance of 10 ohm. Here the tower footing resistance is given as 10 ohms. So here we have RTF at 10 ohms in a soil of resistivity, and similarly the resistivity of ρs is given as 10 ohm meters, and calculate the required dimension of electrode using the most common electrode shape, and assume thickness of 2.5 cm for the rod and counterpoise, and depth of 0.5 meter is given as for the counterpoise. So here we have given data as RTF is given at 10 ohms, similar to RS is 10 ohms meters, similar to the value of A this is 2.5 centimeters, and this is the thickness for the rod, and similarly this is the thickness for y equal to 0.5. So this is the depth of counterpoise. And for hemisphere electrode, here we have the formula as R is equals to rho s upon 2 pi RTF. So you'll get the value of here R means the length here. Here we need to calculate the value of length here. Calculate the required dimension of the electrode. So here R is the length here. So R is equals to 2 rho s upon 2 pi RTF. RTF means rho s is given as here 10 ohm meters. Similarly 10 upon 2 pi, and RTF is also given as here RTF is given as 10 ohms. Similarly rho s is also given as 10 ohms. So 10 upon 10, this is going to cancel. So 1 upon 2 pi. So 1 upon 2 pi will be 0.16 meters. And for vertical rod, we have RTF equal to rho s upon 2 pi L into log 2L upon A, and RTF is given as 10. Similar RS is also given as rho s is given as 10 and 2 pi L. So 2 pi L, we need to calculate the value of L here. So log 2L upon, and value of A is also given 0.025. So from here we will get the value of L as 0.62 meters. And for counterpoise, RTF equal to rho s upon 2 pi L log 2L square upon A into Y, and once you substitute the value of RTF here, similarly rho s is also given, and here we need to calculate the value of L here, and here A and Y is also given in the questions. So once we will solve this, we will get the value of L as 0.689 meters. Now a tower of 735 kilovolt line has a 40 ohm footing resistance and 2 ground wires, each with ZZ equal to 500 ohms, and the lightning stroke source impedance is ZS as 400 ohm, and IS is given as here 50 kilo amperes. First, calculate the tower top potential considering all the impedance, and in B neglecting all the ground wires and stroke source impedance, and in C considering only one ground wires and stroke source impedance. And here in the second one, here we have how should the flashover strength of insulator string be destroyed if the coupling factor between the line and the ground conductor is given as 0.2. So here the value of RTF is given as here 40 ohm. Here you can see in the questions footing resistance. Here you can see footing resistance of 40 ohm is given. So RTF is given as 40 ohm. Similar ZZ is also given as 500 ohms, and here ZS is given as 400 ohms. Similarly IS is given as 50 kilo amperes and NG as 2. So first, in the first case, here we will consider the tower potentials. So considering all the impedance, so here we will consider all the impedance. So ZE will be 1 upon RTF plus 2 NG upon ZG plus 1 upon ZS. So 1 upon, just we need to substitute all the values, since all the values are given, just we need to substitute and calculate. So on solving we will get the value of ZE as 28.2 ohms, and therefore the tower potential will be Vt is equal to 28.8 into 50. So we will get 1410 kilovolt. And similarly here in the second case, neglecting the ground wire and stroke source impedance. So here we have to neglect the ground wire and stroke source impedance. So for that case, here we have directly we could have got we'll get ZE as RTF. So it will be 40 ohms and V2 will be 40 into, since we know V is equals to IR. So in place of impedance we have 40 and in place of I we have 50 kilo, I is given as 50 kilo amperes. So you'll get the value of BT as 2000 kilovolt crest. And in the third options, we have to consider only the ground wires and stock source impedance. So for that, NG will be 1 and ZU will be 1 upon RTF plus 2 NG upon ZS plus 1 upon ZS. So just substitute all the values, will get the value of ZA. So it will be 31.75 ohms. Now B2 will be 31.75 into 50. So it will be 1587.5 kilovolt crest. Now here you can see in the second option, how should the flashover strength of insulator string be designed if the coupling be a factor between the line and conductor is 0.2. So for the second options, here the value of Kf is given as 0.2 and RMS voltage will be 735 kilovolt given. So 735 into root 2 upon root 3 will get 600 kilovolt crest here. And we know Vi is equals to Vt into 1 minus Kf plus Em. So here Vt is given as 2000 kilovolt and in place of Kf we have 0.2 and in place of Em we have 600 kilovolt. So you'll get 2200 kilovolt here. And here we have the next numerical as 3 single core cables are used for a 132 kilovolt 3-phase ground wires lines and the core diameter of cable is 2.5 centimeters and the insulation thickness is 4 centimeter given. Here the core diameter is 2.5, insulation thickness 4 centimeters, and calculate the maximum and minimum electric stress in the dielectric and the total charging kVAr, and the relative permittivity of the insulation dielectric is given as 3.2 here. So here Ti thickness is given as 4 centimeters, so it will be 0.04 meters, and core diameter is 2.5 centimeters, so it will be RC equal to DC upon 2 0.012 meters. Now RSS will be RC plus Ti, so we'll add RC plus Ti, will get here 0.0525 meters, and maximum electric stress in dielectric will get E max equals to V upon log RSS upon RC into 1 upon RC, so you'll get the value of E max. So here the value of V will be 132 kilovolt and Vp will be 132 upon root 3 into root 3, so we will get 108 kilovolt. So here we will use the value of Bp here. So in here we will use the value of Bp, and Emax will be, so 108 upon log RSS and RC is already given in the questions, and we have calculated the value of RSS also, so 1 upon RC. So once you will substitute, we will get the value of Emax, so it will be 6020.55 kilovolt per meters, and since this is in meters and if you divide by 100 you will get in kilovolt per centimeter, so 60.2 kilovolt per centimeters. And similarly E minimum will be V upon by log RSS upon RC and 1 upon RSS. Again we will use the value of here Bp here, so just substitute, you will get the value of 14.31 kilovolt. And also in the second part, the total charging kVAr, the relative permittivity. So here in the second one we have to calculate the total charging kVAr. So for that, here we have the formula. You need to remember a formula. Here for charging kVAr we have the formula 4 pi square f v square epsilon naught into epsilon r upon log RSS upon RC. So substitute all the values, you will get the value of here charging kVAr. So just remember this formula in order to calculate the charging kVAr. And here we have the next one. In a Marcus generator circuit used to generate impulse voltage, each capacitor is rated at 100 kilovolt and 40 nanofarad. The load, if is a load capacitance is given as here 1000 picofarad. If the efficiency of the generator is 98%, calculate the number of stages required for maximum output voltage of 490 kilovolt, and calculate the value of R1 and R2 to generate the output voltage waveform. So 1.2/50 microsecond, and this is our required circuit. And here we have given the value of C, B, C2 and Cg. So the value of C is 40 nanofarad. Similarly, B is given as 100 kilovolt. Similarly, load means C2 is given 1000 picofarad, and Ng means generating efficiency is 98%. So here, and also V naught is given as here 490 kilovolt. Here the output maximum output voltage is 490 kilovolt given in the questions. And here we know that efficiency equals to V naught upon N into V. So here N equals to V naught upon Ng into V, and here we have V naught, V and Ng given in the questions. So from here we will get the value of N. So N will be 5 here. So to calculate R1 and R2, here we have first we need to calculate the value of Cn. So for Cn, C is equals to C1 upon C. So 40 into 10 power minus upon 5 will get 8 into 10 power minus 9 farad. Now waveform time and wave times. So here the formula for waveform time is T1 is equals to CR1 into C1 into C2 upon C1 plus C2. And from here we will get value of R1 since T1 and T2 is given in the questions. Here you can see the waveform and the wave tail time is already mentioned in the question. So this is the waveform time T1 and this is the wave tail time T2. So you have, so once you will substitute all the values, you will get the value of R1 from here, sir. Since T1 is given, C1, C2 is given in the question, so you will get the value of R1 as 450 ohms. So the value of R1 is 450. Now from T2 means the wave tail time, we have T2 is equals to 0.7 R1 plus R2 and C1 plus C2, and T2 is also given, means wave tail time is also given in the questions. And here from, and just we have calculated the value of R1, and we need to calculate the value of R2 here, and also C1 and C2 is given in the questions. So from here we will get the value of R2 as 7486.50 ohms. Now this is also one of the important numericals. This is also frequently asked numericals. A Rogowski coil is designed to measure impulse current, and the current is read by a voltmeter as a potential drop across the integrating circuit connected to the secondary, and the value of mutual inductance, resistance and capacitance to be connected are 2 nanohenry, 2 kilo ohm and 1 nanofarad respectively, and estimate the magnitude of impulse current and the rate of change of current. So here given in Rogowski coil, the value of M is given as 2 nanohenry, value of R is given, similar value of C is also given here. And we know for a Rogowski coil BMT is equals to M upon CR into IT, and here M upon CR will be, here M upon CR will be BMT upon IT. So BMT we have plus BMT we have 2 into 10 minus 9. So here we have M upon CR. So M upon CR will be, here we will use M upon CR. So M upon CR, in place of M we have 2 nanofarad, so 2 into 2 nanohenry, so 2 into 10 power minus 9, and in place of CR here we have C as 1 into 10 power minus 9, and in place of R we have 2 kilo ohms. So here we have VMT is equals to M upon CR, so IT, and so it will be M upon CR. So in place of M we have given 2 nanohenry. Similarly in place of C we have 1 nanofarad, and in place of R we have 2 kilo ohms. So just will substitute the value, will get 10 power minus 3, and VMT will be 10 to the power minus 3 IT. Now we know 1 upon CR is equals to omega upon 10 pi. So from here we will get the value of omega. So omega will be this value, and we know omega equals to 2 pi f. So 2 pi f will be this value. And now from this, so from these relations we will get the value of f. So f will be 2.5 into 10 power 6 hertz, and time period t is given as 1 upon f. So 1 upon 2.5 into 10 power 6, so you will get 4 into 10 power minus 7. and it is appreciated that the rate is for 1/4 cycle of the sinusoidal wave. So t upon 4 is going to give 10 to the power minus 7 second. And considering here the meter reading is not given in the question, so considering the meter reading to be 10 kilovolt, so Vm will be 10 kilovolt, and from 1 we will get here we have Vmt is equal to 10 minus 3it, and we have assumed Vm as 10, and from here using 1 we'll get the value of it as 10 to the power 4 ampere. Now we have the relations I upon di upon dt equals to t upon 4. So from here we'll get the value of di upon dt. So it will be 10 to the power 11 ampere per second. Now this is also one of the important numericals. So here we can see for a 1200 kilovolt ESB transmission line, earthing coefficient is 0.8 and arrestor protection level is 3.0, and the arrestor is located at first at 30 meters, second time at 20 meters, and from the transformer having protective ratio as 1.25 given protective ratio, and check whether the transformer is properly coordinated or not for the two cases, and compare the best result with the explanations. And when the traveling wave of 10 kiloampere, peak value time is 1 microsecond, and source impedance of the line is 350 given. So here all the data is given in the questions. Here the voltage level transmission line is 1200 kilovolt given in the questions. Similar to earthing coefficient is given as 0.8, arrestor production level is also given as 3a, and the distance between LA and transformer. So here we have two distance given. First one is L1 equal to 30 meters and the second one is 20 meters given, and the transformer production ratio is given as 1.25, and the traveling wave ratio is given as 10 kiloamperes, and also T1 as 1 microsecond peak value times given, and source impedance is given as 350 ohms. So these all data are given in the questions. And now in order to calculate the temporary over voltage, so we have 1200. Here you can see this 1200 into earthing coefficient into will take and into 1.05. so for over voltage of plus minus 5%, so we'll multiply with 1.05, so we'll get 1008 kilovolt. Now BIL of lighting arrestor will be means this LAPR. Here we have used these values. Means arrestor production level into voltage level means temporary over voltage. So 3 into 1008 will get 3024 kilovolt. And now BIL of transformer will be given as TPR transfer protection ratio into BIL of lighting arrestor. And here we have obtained the BIL of lighting arrestor as 3024. So 1.25 into 3024, it is going to give 3780 kilovolt. And now lighting discharge current equal to 10 kiloampere in 1 microsecond. This is given in the questions. And voltage source will be I source into ZC, and I source is given as 10 kiloamperes. So 10 into, and ZC is also given 350. So we'll get 3500 kilovolt per microsecond. So this is the value of dV upon dt. And suppose in the first case the length is given as 30 meters, and in the second case the length is given as 20 meters. So first case L1 equal to 30 meters, so here we have V1 is equals to V1 minus Vp equals to dV upon dt into L1 upon 150. So this is the empirical formula. So from here V1 can be calculated as V1 is equals to Vp plus dV upon dt into L1 upon 150, and Vp we have obtained as 3024, and dV upon dt is given here 3500 into L1 upon 150. In place of L1 where we have 30 meters and a 150, so it is going to give 3724 kilovolt. Similarly for L2 is 20 meter given in the questions. So for that V2 will be Vp plus dV upon dt into L2 upon 150. So we'll get, in place after substituting value of L2 as 20 meters, we'll get the value of V2 as 3490.67 kilovolt. And here both V1 and V2 is less than BIL of transformers, therefore the transformer is properly coordinated here. As And again also we can conclude as V2 is less than V1, so better choice is V2, and that is the distance between lightning arresters and the transformer should be L is equal to 20 meters is better here. And here we have the next one. A solid dielectric of 1 centimeter thickness and relative permittivity epsilon r equal to 3.8 has an internal void of 1 mm thickness. If the rod is filled with air which breaks at 21 kilovolt per centimeter, determine voltage at which an internal discharge can occur. So here we have epsilon r given as 3.8 and thickness of dielectric will be this. Once here solid dielectric 1 centimeter thickness is 1 centimeter minus, and here the void is has an internal void of 1 mm given, so 1 centimeter minus 1 mm, it is going to give 0.9 centimeter. So this is the value of d1 here. And now thickness of void is 1 mm given, so this will be thickness of void will be d2, and e2 will be 21 kilovolt per centimeters. Here we will consider this value as a e2. Now breakdown of a dielectric E1. So in order to calculate the E1, we have E2 upon epsilon r. So 21 over 3.8, it is going to be 5.56 kilovolt per centimeters. Now the total breakdown voltage will be here. VAB is equal to E1 D1 plus E2 D2. Here we have obtained all the values. Just we need to substitute E1 D1 and E2 D2. We will get the value of VAB. So it will be 7.07 kilovolt. So this was all for today. Hope you enjoy the lectures. Thanks for watching, and please don't forget to subscribe to my channel. Thank you.